Hello everyone, I am Tsung-Tai Yeh. I am from National Jiao Tong University in Taiwan. Today I'm going to be talking about our idea about the RISC-V cycle level simulator on edge GPU architecture. We see the GPU is used in different domains from this slide. 3D gaming, virtual reality, and 4K video are common applications on mobile phones. The GPU reduces the latency of the compressed computation on these applications to satisfy the needs of mobile phone customers. Furthermore, the GPU also accelerates the object detection and navigation on self-driving vehicles to react changes of dynamic traffic environments. As that, the GPU also plays a critical role on data centers. The GPU provides the high throughput for the training of deep neural network and the scientific computing. This example shows the evidence of increasing demands on GPU computing. Initially, the GPU is specialized for the computer graphics. Recently, GPU becomes a programmable parallel course. Let us look over the evolution over these 2 decades. From this figure, the x-axis is the year. The y-axis presents the GPU architecture generation. From this graph, the throughput has a great leap in every generation. NVIDIA released CUDA programming as 2007. CUDA programming increased the GPU demanding. In the near future, the GPU performance will continue to grow, I believe. But the question is how to create better architecture to keep this growth. GPU are shown in different devices from the edge to high-end devices. The GPU in iPhone is responsible for the acceleration of visual computing. Apple released its own programming, so the people can drive the GPU on iOS by using Apple-specific programming language. NVIDIA Tegra GPU is an integrated GPU, which shares the memory space with host CPU. This Tegra SoC includes ARM multi-core CPU, low-power LDDR RAM, and domain-specific accelerators to accelerate machine learning and image processing. The Tegra has less number of GPU cores compared against A100 GPU because its power constraints. NVIDIA A100 GPU has a large number of GPU cores and tensor cores. This GPU is discrete GPU, which has its own memory space with GDDR memory to offer high memory bandwidth. More and more spatial functional units are shown in the GPU. The GPU is not only specialized for computer graphics workloads anymore. This presents a trend that more and more domain-specific accelerators are included in a chip to accelerate some specific operations. For example, NVIDIA releases WWMA instruction to map the vector matrix multiplication to the tensor cores. However, details of this domain-specific accelerator architecture are not unveiled yet. So this is very sad. Let's move on and discuss the existing GPU ISAs. Most GPU ISAs are not free and are customized for a specific GPU architecture. For example, the PTX is a virtual ISA on NVIDIA GPUs. PTX is similar to the RISC-like ISAs and use a limitless set of virtual registers. As a result, PTX is similar to the intermediate representations used within optimizing compilers. However, some special architecture designs cannot be known from PTX ISAs. The SAS ISA is an actual ISA on NVIDIA GPUs, but it is hard to know their detailed knowledges because NVIDIA did not disclose details of SAS instructions in public. AMD released an RDNA instruction set recently. RDNA instruction set is planned to be used in mobile products and game consoles, and RDNA2 is the latest version. So AMD instruction sets are open sources, but all of them are customized for AMD GPUs, so no flexible to be used in the different IPs. So there are lots of different types of GPU ISAs. So for example, ARM and PowerVR, even a Raspberry Pi, they use a Broadcom video core. So the question is, which ISAs we should use in the GPU research, in the academia? Does the existing open source GPU ISAs open for the innovation of GPU IPs? The cycle-level GPU simulators are widely used in the GPU architecture research in academia. The first example is GPGPU Sim. The GPGPU Sim targets to the NVIDIA discrete GPUs. GPGPU Sim includes the NVIDIA GPU's functional unit and memory models. GPGPU Sim can simulate PTX or PTX plus ISAs. Recently, GPU Sim also has supports the trace-driven simulation. And the GPU Sim also has the chiplet-based architecture and the tensor core model for the machine learning and OpenGL workloads. GPU Sim provides several utilities and models to help the profiling of the GPU power consumption and hardware counter visualization. So the next simulator was from the AMD. So AMD released the Gen 5 APU simulator in 2018. The Gen 5 targets for the AMD APU model and use the native GCN ISA. But the question is, we still do not have enough freedom to define our own GPU and limits to create the AMD-like GPU. So we have had a number of simulators for the RISC-V ISAs. For example, the Spike and the QEMU that aims to verify applications compile and work correctly. Their simulation speed is very fast, but cannot capture the microarchitecture details. RTL simulator can offer low-level microarchitecture details, but the RTL simulator speed is very slow, unfortunately. So even in the small applications, the RTL simulators might take several days to run. So this is very inefficient way in developing GPU architecture. Another option is the FPGA. So FPGA provides an accurate timing simulation, but this approach requires the physical FPGA boards, and then in synthesis, plays the loud process. So the long-time simulation slows down the architecture development time. So the question is, how to shorten the time in developing RISC-V GPU architectures? The hardware simulator impacts on the time of architecture designs. In this figure, the x-axis is the simulator speed, and the y-axis is the simulation accuracy. From this figure, we will see the RTL simulation has high simulation accuracy, but lower speed. On the other hand, the Spike and the QEMU has the fast simulation speed, but their simulation accuracy is very low. And the cycle level simulator is another option to trade off the simulation accuracy and the speed. And this is the option can accelerate the design of the microarchitecture. There are a couple of the cycle level simulators that support the RISC-V ISA on CPU models. So we have had a RISC-V CPU simulator, but unfortunately, the GPU model is missing. A RISC-V GPU was released recently from ThinkSilicon NEOS-V. The NEOS-V is a small GPU with a small number of cores compared to NVIDIA Tegra GPUs. The throughput and the clock rate of NEOS-V GPU cores is also lower than the existing H GPUs. The NEOS-V supports different types, data types, and the computer graphics workloads. Basically, this is a good news and good to know to have the GPU composed of RISC-V ISAs. But the question is, how does the academic research contribute their designs for the RISC-V GPU? Let's move on and discuss challenges on edge GPUs. Low power is a critical issue when designing edge GPUs. From the upper figure, the power consumption is proportional to the number of GPU cores. Compared against the FPGA, the GPU consumes more power and more gasoline on vehicles. Reducing the number of GPU cores won't resolve the edge GPU power constraints completely. So therefore, we need an energy-efficient architecture design on edge GPU to overcome the power constraints on the edge GPUs. These two pie charts show the power consumptions breakdown that was from the GPU watch power model. This statistics was collected from the 25 GPU applications. So in these pie charts, we can see the first, the GTS 480 functional unit, a functional execution consumes more power than the other one, because the increased functional unit and the SIMD width in the GTS 480 GPU. Furthermore, GTS 480 has the large register file size, but the total power consumption of the GTS 480 increases more than register file does. In both pie charts, memory power consumption dominates over and consumes over 50% power on GPUs. The question is there any solutions to reduce the power consumption from the GPU memory? The next challenge of the edge GPU is the latency. DRAM bandwidth is increased linearly over years, but the latency does not. The discrete GPU has separate memory space. The data is required to be moved back and forth between the host and the device memory space. The data movements on the discrete GPU increase the computational latency of applications. On the other hand, the integrated GPU has a unified memory space. The virtual memory manager can handle the memory access from the host and the device. However, the rising of the data movement is becoming a critical bottleneck on edge GPU. So to minimize the GPU application's latency is another critical challenge on GPU architectures. Branch divergence on a GPU occurs when threads inside walls branch to a different execution path. This control flow problem on the GPU increases the functional execution latency and reduces the SIMD utilization. Machine learning and the sparse matrix computation presents massive data parallelism, but the dynamic sparsity increases the redundancy on GPUs. These two problems are also shown in the common computer graphics workloads, such as ray tracing on GPU. So this is another challenge on a GPU. So from the previous the problems we mentioned on the GPU architectures. So in this slide, we try to propose the RISC-V GPU cycle level simulator to overcome the problems we mentioned in previous slides. We aim to define the GPU hardware blocks on cycle level simulators composed of high-level programming languages. So our proposed simulator supports the RISC-V ISA. People can follow or extend RISC-V ISAs to create their own new GPU ISAs from our proposal. Our proposal includes the software stack and hardware simulators. So our proposed modular GPU IP simulators can help for the comparison and validation of different GPU IPs. Our cycle level GPU simulator is faster than RTL simulators. And our simulator can be used in the initial stage of the architecture design. As far as we know, the microarchitecture counters, such as the IPC and the cache keys miss rate, that reflects the runtime characteristics of applications. This detailed architecture statistics also help us to explore the space for the optimization on software and hardware stack. So another advantage of our proposed simulator is the modular GPU IPs. So this feature provides IP benchmarks in the comparison to other architectures. So regarding to the limitations of our simulator is in the GPU model accuracy validation. So the reason why our simulators is limited to the computer graphics workload. One of the reasons is the computer graphics and the visual computation are the most common applications on edge device. So in the first stage or in the current stage, we will target this workload as first. And we will try to extend our design to the GPU programming model, but this is the future step. So we divide these projects into 3 phases. So the first phase aims to modify the software stack to support the RISC-V ISA. So in the beginning, we will collect the multiple computer graphic applications implemented by the OpenGL ES or even from the Vulkan programming API. And we will try to use the API trace for this OpenGL application, or even this NeuroG for Vulkan programming API, and we can get some API trace from these trace tools. And then in the Mesa 3D library, and we will try to converts these computer graphics IRs to the this TGSI implementation. And in the final stage, we will use this, we will insert some our converters to convert the TGSI IR to a RISC-V ISA in an LLVM backend. So in the first phase, we require to change the current runtime in the compiler software stack to enable us to gain the RISC-V ISAs from the computer graphics workloads. The second phase is to integrate the existing GPU functional units, memory, and power models on our simulator. So we will insert hardware counters to collect the details microarchitecture information. We also will run the computer graphics benchmarks on our simulator and validate the correctness of functional units, memory, and even power models. Finally, we will consider the extension of a RISC-V spec for the GPU architectures and do the further validation on FPGA about power consumption. The final goal of our proposal is to work out a SoC cycle level simulator. In general, a SoC includes several different domain-specific accelerators, such as neural processing units, NPU, and GPUs. To achieve this goal, we need to integrate the CPU and NPU model, and even some special instructions from the NPU with our simulator. So we raise some challenges on the CPU model and NPU model and NPU model we might have during the integration. So for example, in the single or multiple GPU, or even this cache coherence protocol in the host and the device heterogeneous architecture, even should we require to support this memory consistency. And in the challenges in the NPU model side is we might encounter this machine learning data flow translation and mapping to this NPU accelerator, and how to mapping and translation, or even some special ISAs used in the current NPU model. So how to realize this integration and translation. So in this slide, it shows that the several potential problems we might encounter during the integration. And we welcome anyone to share us your ideas and the suggestions about this final phase. Let's review the key points from this talk. First, we talk about changes on RISC-V simulators for the GPU and GPU architectures. Our goal is to speed up the innovation of edge GPU hardware with RISC-V ISA. Second, we propose a GPU cycle level simulators with the RISC-V ISA. the simulation time and microarchitecture details of cycle-level simulators that can help the speed of GPU architecture designs. Furthermore, our modular GPU objects can simplify the IP testing and validation processing. Finally, we would like to integrate the CPU and NPU models on our simulator to contribute for the GPU architecture research, the SoC architecture research. Thank you for your listening and welcome to share us your suggestions and feedback. And thank you.